Right, well, thanks a lot for coming today. As you can see, we're going to be talking about getting started with FreeRTOS on LPC microcontrollers. Introduction is always a good place to start. My name is Richard Barry, and I am the founder of the FreeRTOS project. The FreeRTOS project is owned by my company, Real-Time Engineers Limited. We're based in the UK, hence my strange accent. There's a suite of products based around FreeRTOS. There's the open source FreeRTOS kernel, and that's the only bit I really get involved with myself. I also license the code to a global engineering company who supply it under a commercial license. We'll talk about licensing a little bit later on. So it's exactly the same product named OpenRTOS under the OpenRTOS brand, but with commercial licensing. And there's also a safety critical product been through lots of safety certification, which was based on FreeRTOS originally, called SafeRTOS. So these are the three products in the family. So what is this talk about? Well, first of all, I want to make sure we're all on the same page and we know what we are talking about. So the first few slides are going to be saying, well, what is a real-time kernel? What is a real-time scheduler? Make sure we all know that, so the rest of it makes sense. Then I will talk a little bit about what FreeRTOS is. And these two sections are mainly done with slides, PowerPoint slides. After that, I will be doing a bit more of a practical demonstration session. Sometimes the classes, everybody has their own computer, but obviously with time constraints here, you'll have to just watch me do it. But hopefully I'll show you how to find the source code, looking around the FreeRTOS website, and we'll actually use a project and download it to an LPCXpresso board. So we're actually going to run some code on here. We're not going to go into anything in masses of detail and tell you every nook and cranny of how to use FreeRTOS, but my aim is to show you where the code is, overview of what the code does, and point you in the right directions so you can take it further yourself. Okay, so the first part, what is an RTOS? Multitasking is a very familiar concept. Everybody uses multitasking these days, whether it's on their smartphone, Windows, Linux, Mac, iPad, or whatever. So it's a very familiar concept. What we want to do is not turn it off, turn it past, is run lots of applications at the same time on one processor. Now, 5 years ago when I was giving a talk similar to this, you would say only one task or thread can be running at a time. Of course, these days things are slightly different. With multi-core and things like the LPC4300 with 2 cores on. But basically the concepts are the same. So let's pretend we only have one core. The idea is we have 3 applications. When we're talking about real-time kernels, I tend to use the word task because task is analogous to a thread, but threads have very special meanings to people, to certain sectors of the embedded community, especially Linux-like people. So to avoid any ambiguity, I use the word task, but just think of it as a thread. So we have three tasks running. In this graph, if it's not obvious, what we have is time running along the bottom here, and the red lines represent when a task is actually running, when it's actually executing. So what we want is to give the appearance that all our tasks are running at the same time. Whereas in reality, if we only have one core, like on an LPC1700, what the scheduler's job is to switch each task in and out very quickly to make it appear as if everything is running at once. You won't normally see a scheduling pattern like that. It's very oversimplistic. So what's the difference between our general purpose operating systems such as Windows or Linux and a real-time operating system? Well, a real-time operating system generally has to respond to real-world events in a timely manner. So its objective is very, very different, whereas an old Unix system its objective is to share the processing power out as evenly as it can against all its multiple users. A real-time operating system, its main objective is to respond in a deterministic way. So if you have system requirements that have genuine hard real-time, if they are genuine hard real-time, in other words, if you don't meet that requirement, then your system fails, then a real-time operating system is what you need, not a general purpose. So just as an example here, we've got a software system with inputs coming in. Some of these are high priority, as you'd imagine an alarm is. Some of them have to be very, very fast, like hall sensors or resolvers and encoders if you're doing motor control. Other ones are very, very slow. So there are some hard real-time requirements here in that if you're doing motor control, if you miss your timing occasionally, no one's going to know. But if you miss it consistently, then your system's going to be useless, no good. So that's the idea of the real time. So that's where the RT in RTOS comes from, real time. And this is an example of a scheduling algorithm typically used in a real-time kernel. There are other scheduling algorithms, but traditionally you have something called a fixed priority preemptive scheduler. Fixed priority means that the kernel itself doesn't change priorities. It doesn't mean that the application writer can't change priorities. So here's a very brief example of how that type of scheduler will work. And in this example, we have task 1, which is a high priority event driven. Task 2, which is a medium priority periodic task. In other words, it wants to run at a fixed frequency, as often things like motor control do want to do. Task 3 is a low priority event-driven task. Ignore the idle task for a minute. We'll come back to that in a second. So this is just as an example of how the kernel will behave. So in here we have this medium priority periodic task. It wants to run at time t1. It runs, finishes its work, and then goes to sleep. It doesn't want to run again until time t6, at which point it runs again and goes to sleep at time t7. Again, doesn't want to do anything until time t9 over here, so it starts running, but this time, before it's finished running, this event which causes this high priority task to run occurs. Because that task has a higher priority than the periodic task is stopped, the event is processed, even though the periodic task was still running. And that's what the kernel does. It says there's a task of higher priority than the task that's currently running. It's the kernel's job to say, I must run that one now. And when it's finished executing, then the kernel will say, oh, the medium priority task hasn't finished yet, and it will drop down to the medium priority task. And you can see a similar sort of thing happening here, where there's an event-driven task which is stopped, as we say, preempted by a medium priority task. So you've got low priority being preempted by a medium priority preempted by a high priority task. It's that simple. In this scenario then, what we're saying now is that tasks only execute when they want to, when they have something to do, when there is some processing to be performed. That means you don't have to do any polling of any inputs. I mean, you can if you want, but it's much more efficient to be event-driven in this sense. So if you're not polling all the time and tasks are only executing when they actually have something to do, there's a lot of dead time on the processor. And there always needs to be something to execute. So the idle task is created by the kernel itself. If there are no application tasks to run, then the idle task will run automatically. And you can do all sorts of things with the idle task. A very, very common thing to do is just put the processor into a low power mode. So you've got automatic way of saying, whenever there's no processing to be done, I'll put the processor into a low power mode. You can also put application code in there if you want. If you've got background processing that just wants to run anytime there's nothing else to do, then you can put it in the idle task as well. Okay, so implicit in what I've said is that a task can exist in multiples of different states. So when a task is created, it enters the ready state. And what that means is it wants to run, but it's not actually running yet. So there can be multiple tasks in the ready state. There can only be one task in the running state. So the kernel will look at all the tasks in the ready state, find the highest priority, and put that into the running state. If there are lots of tasks of equal priority in the ready state, in FreeRTOS at least, it will time slice between them, so they will all share the CPU. Once it's in the running state, if there's a task of equal priority, it might just get moved back into the ready state by the kernel. Otherwise, at some point, it's finished its processing. It then wants to wait for the next time it needs to process or the next event to come in. So it will move down this transition into the blocked state. When it's in the blocked state, it's waiting for an event. When that event occurs, it might be a time that comes along, or it might be an external event. It might be another task sending it a message, anything like that. The kernel will then move it from the blocked into the ready state. If it is then the highest priority task, it will immediately move into the running state again. And these are the states that the task will spend most of its time in. There is also a suspended state. That's not so common to use that. There are certain applications that would want to use that. Implementing select statements in TCP/IP, for example, is a very common use of the suspended state. When it's in the suspended state, it's like the blocked state. The kernel knows it can't run, but it's not waiting for an event. The only thing that will move it out of the suspended state into the ready state is another task making a function call to say, unsuspend this task. All right, so I think hopefully I've given a very, very quick top-level overview of what a real-time kernel is and what a task is and what a task does. When we look at the example, I will actually show you some source code of implementing a task and the API functions and things like that. So I appreciate I haven't actually shown you that yet. So why might we want to use a real-time kernel? So the mythical, typical example that doesn't really exist. What I've tried to do here is show lots of conflicting requirements in one application that you might quite often come across. And these are deliberately chosen to show these challenges in this system. So in here we have some software which is converting data and writing to an LCD. So we have an alarm annunciator, an ADC input, maybe just a keypad input, but they all want to write to the same peripheral. So there's a conflict there. Communication and control with a very fast, very accurate requirement for a motor. So we're taking a timer input and we're taking motor position data. Very high frequency, very fast, high accuracy requirements. Here we have some formatting of data which is being written to a flash disk. So this is a very, very slow device. This is a very, very slow device. The motor is a very, very fast device. So problems. CAN bus protocols, again, timing requirements can be very strict. So the real-time requirements here, very strict real-time requirements here. No hard real-time requirements here at all, really. So you can see there's a good mix of requirements in this system. Some of it's event-driven, some of it's periodic, some of it's continuous processing. Different characteristics of each part of this system. So how can we implement this? And the answer to that is, of course, there are lots of ways you could implement it. Only one of which is with a real-time kernel. And even though I go about my life evangelizing FreeRTOS and promoting FreeRTOS, I'm not someone that says, thou shalt use a kernel all the time. It's always about using the best tool for the job. So at some point, using a kernel will become the best way of doing it. This is, by the way, don't complain you can't read this because I've deliberately made it so you can't read it, hopefully, because what's written in there is irrelevant. It's just the concept of what it's trying to show. So here we have a sort of foreground, background, Superloop type implementation where you have a little flowchart or state machine which is implementing one piece of functionality, which then moves on to another little flowchart or state machine that then moves on to another little flowchart or state machine. When that's finished, it goes back to the beginning, and it sequences through like that. It's processing all the time, and probably polling inputs, or if there's nothing to do, it'll be on a spin looking for a timer. Each of these state machines or flowcharts will have to maintain state. Calculating the timing is very, very difficult. In the full version of this talk, I've got a classic example of this, of a state machine to control the timing on an LCD display, which was genuine code written by a semiconductor manufacturer, not NXP, I hasten to add. But, and the challenge then is to try and understand what it's doing at all. And then you also have interrupts processing. So, a perfectly valid way of implementing a lot of applications. But the question is, will it scale? If you have new requirements into this, if the speed, if you, as often happens, your display is obsoleted and you have to put a different display on there, the speed of that display is different, how does that affect the rest of your code? The timing of the rest of your code? And really the point, I'm not going to go through each point here in great detail, but the point I'm trying to make here is there are a lot of problems with doing this type of application with regards to maintainability, scalability, code reuse, that sort of thing. So we've got all these little faces over here which are just supposed to symbolize either very bad or moderate. And the idea is we're going to look at the same application, or a very small part of the same application, using a kernel, and we're going to turn all these smiley faces, or turn all these grumpy faces into smiley faces. That's the idea. Okay, so we've looked at the sort of, if I can call it, traditional foreground, background processing, Superloop type of application. But in this mythical, typical application, we've got a lot of requirements, a lot of communication interfaces that we have to process. So how would we do this using a kernel? Now, we can't go through the whole application design, so I've taken what I think is probably the most complex part and shown a typical sort of design that you might come up with. So if we have our, I don't know, it's very, very common to do motor control, so I'm sort of assuming that a good proportion of people in the room are familiar with motor control, but if you're not, it's common to have a sort of outer loop control with sort of millisecond resolution where you're calculating what exactly you want the motor to be doing, and then having an inner loop control which has to have microsecond resolution, which is doing the actual motor control according to the commands of the outer loop. And then you have the actual physical output to the motor, maybe a PWM or something like that. So in here I'm saying outer loop control we can do in a task. Millisecond resolution's fine, we can do that in a task. Inner loop control, microsecond resolution, it's a bit fast for a task. Probably done in an interrupt. Maybe there's a timer interrupt or an interrupt off one of the, so I've shown the examples here, hardware timer interrupt or off one of the position sensors on the motor. You might be doing commutation or something like that. And then the physical continuous output done by the peripheral itself. So this task might then talk to a CAN bus task, and it might talk to a human interface task. And FreeRTOS provides, or I say FreeRTOS, kernels provide mechanisms for tasks to communicate with each other. And tasks and interrupts to talk to tasks as well. So here's a little flowchart now of our CAN bus, motor control, outer loop motor control task. So again, it's a sort of sequence or a state machine or however you want to code it. Start off, it's going to look at the human interface. It might be TCP/IP it might be a keypad, could be an RS-232, command console, anything, where the user is either monitoring variables or updating variables. It's going to process those. It's then going to wait for the next control cycle. I said millisecond resolution. It has to execute, say, every 4 milliseconds or something like that. So this is an example of a periodic task. And this is a FreeRTOS API function here. Normally I stand by the screen and point at things. It's a bit easier than using this. Here is a FreeRTOS API function which is used to create a periodic task. Just to explain this a little bit, the X denotes the return type. Task tells you where that function is defined. So in this case, it's in tasks.c. And delay until is quite a verbose way of telling you what the function does. Tend to have very verbose function names, which some people really like and some people really hate. But I don't like cryptic acronyms myself. So it's going to wait until the next control cycle. The next control cycle comes along, so the kernel moves it into the ready state. It then sends out a sync message on the CAN bus, for example, and it then has to wait. The sync is basically a timing message to all the other motors on the system. They're going to reply with their positions on the assumption that what the motor this is controlling is dependent on other motors' positions. It doesn't have to be motors, it could be sensors on the CAN bus, could be anything. So it then has to wait until the answers come back. So here's another FreeRTOS function, quReceive. Again, X is the return type, Q is because it's defined in Q.C, and receive because you're receiving data. And this is a blocking FreeRTOS call. Now, by blocking, I don't mean that it's spinning on something and not returning. When it's blocked, it's not executing. That means other tasks in the system can execute. So if there is a TCP/IP stack which is sending data into this, then that can still execute whilst it's waiting for messages. A message comes in, an interrupt will unblock the task. The task will say, have all the motors or all the sensors responded yet? If they haven't, it will go back here and wait. If all the sensors, or if all the data it needs to do its control cycle are in, it will then execute its outer loop model, update the PID parameters which are being done in the interrupt service routine, and then go back up here, handle any HMI, human interface commands that have come in, and then wait for the next control cycle. So quite simple, very little dependency on anything else that's going on. Just check the time. So going back to our task states, what's happening here is it's in the ready state. It runs. It says, oh, I want to delay until a time, so it goes into the block state. That timing event occurs, so it moves into the ready state. It's the high priority task because it's doing the motor control, so we'll assume it's the motor control. I'll just finish this bit, then I'll get your question. Okay. So then it sends out the CAN message. It's sends out the CAN message, calls another blocking function, moves back into the block state. CAN event comes up, goes through the ready state into the running state, processes, and when it's finished, calls task delay until again, and it's back into the block state. What's the benefit of the task-based implementation compared to the Superloop-based implementation? Now, if you can imagine trying to do that same scenario in the Superloop whilst you're handling lots of other things, compared to that, in this example, we've completely decoupled our motor control from anything else that's happening in the system. You might be writing to a flash disk somewhere else, or the speed of the LCD might change, or the speed of your processor might change, put a different crystal on it or something like that. Doesn't make any difference. The kernel is managing all the timing, and the kernel is making sure that this high priority task is always the one that's running, no matter when it wants to, that is, no matter what else the system is doing. So as far as, well, all the things I've listed on here go, you've improved your scalability of the system. You have a decoupled, functionally cohesive tasks, which are reusable, hopefully. and you've decoupled the timing from the functionality. And really, I think one of the primary things in software is maintenance. How maintainable is the design you come up with? Because that's ultimately what's going to make the difference. So we see we have some green smiley faces, still some amber faces, but the situation has improved. Okay, so we've looked at briefly what a kernel is, very briefly at why you might want to use one, on the understanding that you don't always want to use one. And now we'll look at what FreeRTOS is. So FreeRTOS is it's in the name really, it's a free RTOS, which is completely open, downloadable from freertos.org. We'll look at the website and how you download it a bit later. It's an extremely popular kernel for the type of microcontroller that we're talking about today, the sort of Cortex-M class of microcontroller. It's a very, very good fit for that. Consistently comes top in all the sort of embedded market surveys, downloaded 170,000 times in the last 2 years combined. So you can imagine that even if a very, very small percentage of those downloads turn into a product, that is an awful lot of products in the world that are running FreeRTOS. We don't have time to go through all the features, but if you look at the website, then you'll see the features. If you read the book, that goes into a lot more of the features as well. Supports 31 different architectures, so that's counting Cortex-M3 as one architecture. It's counting ARM7 as one architecture. So you can see how many other architectures it supports, 17 different tool chains. One of its value propositions, if you like, is there's absolutely no lock-in to anything. It is portable across platforms, across tools. And this graph is just supposed to show the sorts of processors that it runs on. So it's very difficult to quantify these dimensions, especially the applicability dimension. But if you imagine down here, we've got slow CPUs like, I don't know, 8051. Up here, we've got Pentiums. Somewhere in the middle, we've got Cortex-M class 32-bit processors. Oops. It runs on 16 and 8-bit as well, I have to say. But this is really the area where FreeRTOS fits. It's an absolute perfect fit for Cortex-M. At this end, you can run Linux, Windows CE, or whatever the latest version of that is, all the, QNX or all those other large systems. At this end, you're never going to want to use a kernel because the types of CPU you're talking about, you'll never write an application that needs a kernel. So this is really the area we're talking in. It's specifically designed for microcontrollers. So code size is one of its primary objectives. And I'll have this slide in here because it's a question everybody always asks, except today, because no one's asking questions. Is it free? Yes, it's free. Can it be used in commercial software? Yes, it can be used in commercial software. What are the license terms, and is my proprietary code at risk if I link to FreeRTOS? No, it's not, is the answer to that. So think of the FreeRTOS API, which is supposed to be represented by this green bar here, as being the boundary. If you have the FreeRTOS kernel code, that is open source. If you have application code, your own code, or driver code, which might be produced by NXP, or if you have middleware code, which is on the other side of the boundary and just using FreeRTOS, then that can stay completely closed source. Just to mention, there is an ecosystem around FreeRTOS as well. This is just a screenshot of a trace tool that we have. There is a free version of the trace tool, I hasten to add. It is a commercial tool, but the base trace as it is comes in a free version. No restrictions on it. Right. So how did I do? I went over by about 3 minutes, which is pretty good. So what I would like to do now is talk less and show you a little bit of the FreeRTOS website, where you can get the source code from and that sort of thing. So these are the things we're going to look through now. I'll show you the website first of all, and we'll talk through the source code. We're going to be using the LPCXpresso IDE and the LPCXpresso hardware. The IDE is a free download. So everything that we're using here is either free or extremely low cost. These are free to you today as well, but they're normally about $25, $30, yeah. So they're practically free. So the FreeRTOS website is not particularly pretty, okay? It normally looks a lot better than this because the resolution is, I've made the resolution so you can actually view it. So the first thing on here to look at is the menu on the left. At the very top, we have a quick start guide, and that's going to go through a lot of the things that I'm going to show you now anyway. But just to show you it's there, tells you a little bit about locating documentation, how to get the source code, building a project, running demos, and then some links to other useful areas on the website. So that is there. I've put it as the first menu item, so hopefully people read that first. Of course, the thing they always do first is click the download link. On here we also have an API reference section. So I've tried to break these down into logical groups of functions. So task creation, task control, task utility functions. If you expand these, you'll see that there are API function names listed there. At the top there, you will also see that there's a PDF reference manual, which is $30, I think. I would obviously encourage you to buy it. The API reference is online as well. The PDF reference manual has been edited and is probably a bit more, yeah, let's just say it's edited. It wasn't wholly written by me. It might be more understandable. Down at the bottom here, we have very importantly, a link to the free support forum. It's a very active forum. I'm told that the support for this product is a lot better than for commercial products. Couldn't possibly comment myself, but that's what I'm told. There's also an FAQ, and I would like to point out one thing in this FAQ, whereas my application doesn't run. There's a whole load of things here to look at as to why, if you find your application is not running, look at this bit first, see if there's anything in here which will give you a clue as to why, and then if you can't find it, then you can ask a question on the support forum. I would say it's a very important point that if you're creating a FreeRTOS project, please don't try and do it from scratch. The whole concept of this is that every port comes with a pre-configured demo. It has all the correct source files included, it has all the correct configuration, it has the configuration file for you there as well, it has all the correct compiler options and that sort of thing. Start with something that exists. You can then get that running and you have a known good system. You can then start taking out the demo code and putting in your own code. The download link is very close to the top as well, although people still ask me where it is. If you click on there, you will see the link to the download is just there. The download is hosted at SourceForge, so if you click on there, I think you'll probably get directed to the SourceForge site. I can't click on it now because I'm not really online, I'm just running a local web server on my machine. I'm not sure whether the download will start automatically or whether you have to click again on SourceForge, but that's where the source code is. Right, so now on to the demo application. Now, if we go to Getting Started, we see there is a demo project. I'm hoping you can see this at the back. No one said you can't. And here, oh, actually, before we do that, let's look at where There's a whole list of supported MCUs here, and I have to be very politically correct and click an NXP one, as NXP are sponsoring this session. And you'll see the demos for NXP parts there. So if I click on one of those, you then get to a documentation page which is specifically for that demo. Now this documentation page will tell you how to locate the demo in the source code, very importantly, how to open the project, how to build the project, what the project does. Obviously it looks better on a higher resolution screen. How to set up the hardware, how to configure the interrupt priorities. Again, there's a big bit here saying, attention please, to try and trap the 90% of support requests before they happen about interrupt priorities. So these are fairly comprehensive demos, but the one we're going to look at today is under this heading, Basic Demos. And these are very simple examples because people often say that my examples are too complicated. The examples try and show you every feature that there is. So there's lots and lots of tasks created. The feedback is often that's too complex. So what I originally did was have a couple of demos which are much, much simpler. What I tend to do now as new demos are added is actually have two, a simple version and a more comprehensive version. So the source code we're going to look at now, you can just download off the web here. There is an application note that goes with it there. And I'm not going to click on this again now because I'm not really online, so it won't download it, but I have it on my machine already. So that zip file there, and if we open up LPCXpresso, I mean this isn't a tutorial on using LPCXpresso, but just to explain what I'm doing, we're going to import this project into a workspace. LPCXpresso being Eclipse-based has this idea of a workspace, which is a sort of container for projects. So I'm going to create a new workspace there, just a temporary one. And then we'll show you how to import this, and we'll look at some of the source code. So it's an existing project, so I'm going to say import. Again, I hope this is big enough to view, but I'll tell you what I'm doing. Like I said, I can zoom in if anyone wants me to. So I'm going to say I want to import an existing project. And in this case, it's a zip file, so it's in an archive. I'm going to browse to the archive. I'm being prepared. I have it open here so I can do it quickly. Put the path in. And here we have three projects. So there is the CMSys project, which it's dependent on. That's provided by NXP. The FreeRTOS library, so in this case the source code is built as a library. And here is our simple demo, which is the application which uses the FreeRTOS library. So I'm going to import that. And I'm not going to start this building, which isn't going to take too long, but whilst that is building, I'll give you a whirlwind tour of the source code. So when you download FreeRTOS, you get a single zip file, and that zip file has got the source code for every single port and every single demo application in it. So you think, wow, there's a lot of files in there, it's a bit overwhelming. Whereas really, you only need very few of the files that are in there. So the source code is split into two primary directories, one called source, which has the FreeRTOS kernel code in, and one called demo, which has all the projects. We just looked at the documentation for a single project. So if we zoom in on the, or go into rather, the source code project, you will see that there are the FreeRTOS kernel is implemented in three files, really. You've got list.c, queue.c, and tasks.c. That's just three files which are common to every single port. Coroutines are less relevant to this class of processor. Timers implements software timers, but it does it by using the functionality which is in the other three files. So while it extends the API to users like yourselves, it uses the kernel itself rather than being part of the kernel implementation. If we go into the portable directory, you will see there's a directory for every single compiler that's supported. If I go into the GCC directory, you'll see all the processors that are supported under GCC, and the one we are going to be using is that one. So we're using the GCC Cortex M3 port. I mean, the project's already configured to use that one. I'm just showing you so you know your way around the source code more than anything else. Because engineers like to nose around. If I look in the demo directory, you will see that there are lots of pre-configured projects. To find the project, the documentation page will tell you which directory the project you want is in. So we can again have a look here and see that there is there are a few LPC1768 projects in here with different compilers. There's Red Suite, Rowley, IAR, 1768 projects, and the one we're looking at now, or going to look at the simple demo, is an LPCXpresso one. So that should have built, yes, without any problems. Let's plug the board in. Well, actually, I'm going to have to. That's right, I don't need that anymore. I need more USB ports on my laptop. So the debug interface is built in onto the board, so all I need is a USB cable, which is nice. So I'm going to stay up there. So let's have a look at the code that we're going to run. Generally, the way these demos work is that main will create all the tasks and then start the scheduler. Once you've started the scheduler, main never runs again. The stack that was used by main is then used by the interrupts, so you don't waste the stack. So the first thing this is going to do is create a queue. The queue handle is being returned here. That's just going to go off the screen in a second. So here we have the API function to create a queue. XQ create. Again, hopefully the function name is self-explanatory now. Oops, that's not what I wanted to do. And in this example, we have the queue length, how many items the queue is going to hold, and we have the size of each item that we want to hold in the queue. Things are copied into the queue because it's the most flexible way of doing it. If you're queuing integers or something like that, then you want to copy the whole thing into the queue. You don't have to worry about memory, who owns the memory. If you want to queue big structures, then you can just queue a pointer to the structure. So it's a very flexible way of doing it. So that's the queue that our two tasks are going to communicate on. And if we look at how we're creating the task, now, creating a task is the most complicated API function, unfortunately, but it's the one you have to learn first, because without creating a task, you can't do anything else. And if we look at these parameters here, the first parameter here is the function that actually implements the task. We'll look at that in a second. The second parameter is the name we're giving the task, and the name is purely for our own benefit. The kernel does nothing with that. It's just a human readable name that makes debugging easier, because without that, all you get is a handle, which is basically a 32-bit pointer. Third parameter then is the stack size that we're allocating. And the stack size is or this constant minimal stack size is the constant which defines the stack used by the idle task. Now, if you're adding code into the idle task, you might need a bigger stack for it. Here, our tasks are not doing much. They're very simple, being a simple demo. So we're using the same stack size. If you're doing large function called depth, or you're using horrible GCC library functions that use masses of stack, then you will need a bigger stack. Third parameter there is the parameter which we're actually passing into the task. So when you create a task, you can pass a parameter into it as well. In this case, we're not using the parameter, so I've just set it to null. It can be anything. The priority that we're assigning in FreeRTOS, the maximum number of priorities is configurable by a constant in FreeRTOS config.h, which we'll look at should have time. So you've got, if you set the maximum number of priorities to, for example, 10, then 0 is your lowest priority and 9 is your highest priority. The idle task is priority 0. And the last parameter there can be used to pass back a handle to the task. Should you want to do something to that task, like delete it or suspend it or change its priority from a different task, then you need a handle to it. In this case, we're not using the handle, so I'm just passing in null. So we're creating two tasks here. There's a queue receive task and a queue send task. Oh, just before we do that, let's have a look at this. You can see the prototype for the function there. Every function that implements a task, and tasks are just implemented by C functions, must have this prototype. So it's a void function, and it takes a void pointer as the parameter. So that's the parameter in this case we've just set to null. You can use that to pass in integers if you want, or you can use it to pass in pointers to other structures or whatever you want. And typically a task will be an infinite loop. Here we can see a for loop. So this task is just going to go round and round this for loop. If you go off the for loop and you just want to drop off the end of the function and think that's going to delete your task, it won't, all right? It will just crash if you do that. If you want to drop off the task function, then you have to explicitly say task delete at the end of the function, so everything gets cleaned up nicely. And this is a periodic task, so we are calling this function that we've seen already, delay until, and these two parameters just give it the frequency at which it wants to delay. And once it's woken up, it's going to send a message on the queue that we've already created. Here is our other function. Again, you'll notice the same sort of structure. It's an infinite loop. We've got this for loop up here. This time we are calling queue receive. And at the end of there, you can see the first parameter is the queue we're receiving from. The second parameter is the buffer into which that we are going to put the data. And the third parameter is our block time. In this case, I'm saying I want to block forever. You can say I want to block a maximum of 10 milliseconds. And if no data arrives, then the task will carry on anyway. In which case, you have to check the return value to know whether you actually received anything or not. In this case, I'm saying I don't want to run ever until something's arrived on that queue, so I don't have to bother checking the return type because I know something was received. And then it's, if something's received, it checks the value that's received, and if it's 100, it should toggle an LED. So we have one task which every 200 milliseconds is sending the value 100 to the queue, another task which is receiving the value 100 from the queue, and if the value is received correctly, toggles an LED. So what we should find is that the LED toggles every 200 milliseconds. So we'll try downloading that. So I've got this plugged in just via the USB cable and this little debug button up there.
Oh, okay. Try that again. Nothing like preparation, eh? So it's programming the flash, and we're going to run it, and lo and behold, the LED flashes. And that's the most code you'll ever write in your life to flash an LED.